All right, so we are in time, so let's do attendance from here. So we are almost done. We just even we don't take one lecture for one topics anymore. You see, this chapter is pretty short. Yeah. So what I do here today is we finish the gaseous state in last class. So some of the equations, so we can review those a little bit in exam review period. Yeah. So let's work with the liquid state. So you already know what solid, liquid, and gaseous means. So I told you. So mm so if you look here, pen. So if you look here, so this is a beaker you have. So you have three beakers like that. So in this one, let's say in the solid, let's say you put 1 gram substance. So the particles are really close to each other. So it looks like this, right? So those particles are attracting each other, touching each other, and they are not free to move. Everybody see that? So that's a solid. That's a solid. But if you look this liquid, so this pi particle would be one here, one here, one here, one here, one here. Pi particle are like that. So the particle are a little bit far away from each other in the liquid, so they are free to move. Everybody see that? Now if you look this gas, in the case of the gas, this pi particle would be 1, 2, 3, 4, 5. Rapidly moving, they are far away, right? Everybody see that? So this one we finished about the laws of this guy. We already finished in the previous chapter. So we are working with the liquid in this class. Everybody got that? So now let's see what I have here with the liquid. So if evaporation and condensation occur at equal rate, it is called equilibrium. So what it is saying is that, so let's say I have a liquid here. So I have like this. So if, do I have something here? All right, look here. So if the molecule go away from here in the vapor, it is called evaporation. Evaporation. Everybody see that? What is evaporation? If the liquid molecule takes some energy and go away as a vapor, that's called the evaporation, right? Everybody see that? We already know this, right? Evaporation. Now, if you put some cooling agent here in the here, let's put some tube inside. You put the ice, and then this vapor goes there, and then that vapor get cooled because you have ice there, and you can see some water droplet here, and the water comes down. So that is called the condensation. Everybody see that? So evaporation and condensation. So what happened is uh, you have the liquid, and then in the liquid the molecule is sitting like that, but this molecule, the surface molecule, the top molecule gets some energy or more energy, and they just get out as a vapor, and this process is called a vaporization. It happens from the surface, yes, not from the bottom. And if this molecule that going out molecule are cooled by some reason somehow, if you cool them, they come down as in the liquid like that. So this is called condensation. So if the liquid goes as a vapor, it is called evaporation. When the vapor comes down and becomes liquid, it is called the condensation. Everybody see that? Yes, condensation. All right, so what is equilibrium then? So if let's say you have a clock, and in 1 minute time, let's say from this one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, how many, I don't know. So let's say you have a clock, and in 1 minute time, three particles go out as a vapor. How many go out as a vapor? Three particles go out in 1 minute time. You have a clock also. You see that? In 1 minute time, just three particles go out as a vapor, right? And you still have a clock, and in that 3 minute, all three molecules come down within that 3 minutes. So this condition is called equilibrium. Everybody got that? So what is equilibrium? Equal. In the equal time, equal number of molecule goes to vapor, and in the same amount of time, equal number of molecule from gas become liquid. So this condition is called equilibrium. Everybody got that? So equilibrium is very, very, very important concept. So in future, if you can take the Gen Chem 2, so you will be studying a lot of equilibriums. Yeah. So the going out and coming in rate is same. So for example, I have a clock, and I'm looking here 5 minutes. Within 5 minutes, if 10 students go out, and 10 students come in, that is called the equilibrium. Equal number of people go out and equal number of people come in the equal amount of time. Does that make sense? Yes? All right. Now if you look there, so this is liquid, and the liquid is going, some molecule is going to the form of the gas, and some of the molecule are coming back, the gas molecule are coming to the liquid. And if you look that, if these are 5 molecule going out in 2-minute time, 5 molecule of these are coming in 2-minute time. So this is called equilibrium. Everybody got that? Equilibrium concept is very, very important. Now let's go here. So I already told you evaporation and vaporization, meaning that, so you have a liquid, so if you heat it or if you give some energy, these guys from the surface go out as a vapor, that is called vaporization. So enough kinetic energy, meaning that you need to heat it. Yes, sometimes they themselves do, but most of the time we need to heat them to evaporate. For example, if it is a perfume or alcohol, it itself flies away. But if it is a water or some heavy molecule, we need to heat a lot. That's a kinetic energy we need to provide. Everybody see that? Now, condensation, when if this outgoing gas, if you cool it by putting some cold cold tube here, this gas molecule become condensed and come back as a liquid. That's called the condensation. Everybody see that? Yes? So why something become cold? That's called the exothermic process. It gives its heat out, so that is called the exothermic process. Everybody got that? So vapor is hot, vapor is hot. So if you make the vapor liquid, that the heat of this vapor goes out. So therefore we call that as a exothermic process. So if the vapor is always hot, if you try to make the vapor the liquid, so that vapor gives some heat out, and that is called the exothermic process. What is exothermic? We give heat out. Everybody see that? So I'm talking a lot and my body is becoming hot, meaning that I'm trying to give heat out. Yes? So that is called the exothermic process. Good? All right. Now look here. I show you here the equilibrium process here. If you look here in this figure number 1, how many molecules are going up? 1, 2, 3, 4 molecules are going to the vapor from the liquid. Yes? So this is not the equilibrium, only going up. Everybody see that? Everybody is coming in just like that. It's going out. So this is not equilibrium. Not equilibrium. This is not I'm interested in. Now if you look the second figure, the 3 molecules are going out in 1-minute time, and 1 molecule of vapor coming into the liquid in 1-minute time. They are not equal. So I am not interested in this situation. Everybody see that? So I am interested in this situation. If you look here, there are 1, 2, 3 molecules are going to the vapor in 1-minute time, and 1, 2, 3 molecular gas coming to the liquid in 1-minute time. So they are equal. So I am interested in this situation, and we always study chemistry in the equilibrium condition. Everybody see that? So this is not important for me. This is not important for me. This is the important that I'm interested in. All chemistry, physics, everything. The equilibrium is so important. Everybody see that? So we need to look how many people are going out. Oh, 5 people are going out. Nobody is coming in. I'm not interested to study that system. Yes? 5 are going out. 2 are coming in. I'm not interested to study that system. 5 are going out in 1 minute and 5 are coming in 1-minute time, and I'm interested to study that system. Everybody see that? So equilibrium is so much important in studying the chemistry. Everybody got that? Yes or no? So I will put this picture in exam and I ask you which condition is equilibrium and which are we interested in study in the laboratory situation. Everybody see that? So this guy. Yes? Good. Now let's go. So 1 and 2 are not equilibrium condition. Figure 3 is the equilibrium condition because 3 molecule 1, 2, 3 are going into the vapor in 1-minute time, and 1, 2, 3 are coming in, the vapor are coming into the liquid in 1-minute time. Therefore, that is the equilibrium. Everybody got that? Equilibrium is so important. So how do you know if equilibrium is reached or not? So what you should do is, you should go to the lab, put some water here. Water, liquid, yes? And then cover this, and just keep waiting. Just immediately don't start to count. You wait 1 hour, 2 hour, 3 hour, 5 hour, and after 5 hours you start to count how many going here, how many coming down. So you need to just keep waiting to be equilibrium. We don't do anything. Everybody see that? So did I bring you here? I didn't bring you here. I already come here and sit. and one come and another come and another come and I was just keep waiting until 2 and I started my job. You see that? So you just keep waiting before you start measuring. You got that? Yeah, like this. Good. So we just keep waiting the equilibrium reach itself. So that's very important concept. Now let's look the boiling point. What is boiling point? So boiling point means look here. So this is a water. This is water. So this is water. So what happened is that um, I just put it here. How long? Long time. Equilibrium. You see that? Long time. I need to put in equilibrium here. So this one, some molecule are going out, some coming in, going out, coming in, two going out, two. So I am in the equilibrium condition. So this condition, if I put the pressure gauge here, I call this as a vapor pressure. Vapor pressure. Everybody got that? Vapor pressure. So I just put water there in the beaker, and then I close this beaker like this, and I put a pressure measuring device here, and I keep waiting. So maybe at the beginning this guy shows 0.5, after 1 minute 0.2, 0.9, 0.10, and it is about 1, and always keeping 1 all the time, meaning that equilibrium is reached. Everybody got that? That's equilibrium is reached. So at that condition, that is called vapor pressure of the liquid. Vapor pressure. Vapor pressure. Everybody got that? What is vapor pressure means? Yes or no? Yeah. So put the water in the beaker, cover it, put a pressure measuring device, and keep waiting for a long time, 1 hour, 2 hour, 3 hour, and after 3 hour, pressure becomes same all the time, one. Or if you taking another liquid, two, all the time, two. Yes. So that means you reach the equilibrium. So that pressure is called vapor pressure of the liquid. You got it? Vapor pressure. Now what is boiling point? So what happened is this, there is a air pushing this liquid down. So let's say here, so you have a liquid here, and there is a some, let's say 3 molecule are going up, 3 molecule are coming down. So I am in the equilibrium condition, right? And I measure the vapor pressure, and that vapor pressure is called the water vapor pressure at that condition. Now what happened is that, so this water molecule pushing up and down in this condition here, so there is a vapor, and this vapor are pushing this liquid down like that. At the, and at the same time, or you can say up. So either way is fine. You see that? So there is a liquid, and then you can say, oh, these are going up like that. So this molecule, the vapor molecule, are pushing the system up. You see that? There is air. So there is air here, air. So this air are pushing this liquid down. You see that? When this pushing down and pushing up pressure become equal, then that is called the boiling point. Everybody got that? Yes? So you have a water molecule are going up. Yes? So they are pushing air up. And at the same time, there is a air up there, the air is pushing the liquid down. Yes? And when up pushing force by the vapor of the liquid becomes equal to the down pushing force by the air, that condition is called the boiling point, boiling of the liquid. And at what temperature up pushing force by the vapor becomes equal to the down pushing force of the air, that temperature is the boiling point. Did it make sense? Yes or no? So what you should do? So what you should do is, basically you have a liquid here, you have a thermometer here, and then so maybe you are heating it here. So the air is pushing it down maybe by 5 atmosphere pressure. So when the liquid get evaporated, and then they are also giving a 5 atmospheric pressure. And what is the temperature here in thermometer? That temperature is called the boiling point of the water. Everybody got that? So 3 things we are looking. Water is evaporating in, giving pressure up. Air up there we have air. Air is pushing liquid down, and I have a thermometer there. And at certain point, air in up pushing by the water vapor, it becomes equal to the down pushing by the air. And I look the thermometer, and that thermometer temperature is called the boiling point of the water. Everybody got that? Yes or no? All right. So that's how we define the boiling point. Good. Now, this is a liquid and solid phase. So what is the liquid and solid phase? Let's say you have the ice here. So this is ice. And then ice is continuously melting to be liquid. You see that? This is solid. Yes? Ice is solid, right? Yes or no? Ice is solid, so it's continuously melting to give liquid. At the same time, liquid molecules are just coming closer and becoming ice. And when the ice, the rate of melting of ice becomes equal to the rate of freezing of liquid, then that condition is called the another equilibrium, solid liquid equilibrium. Everybody see that? Just like the vapor liquid vapor equilibrium, this is also another equilibrium, solid vapor equilibrium. Yes. So you have water you put in freeze. At the beginning, what happens? Some water molecule come close and try to be ice, and at the same time that ice is trying to melt to give the liquid water, and at the certain time melting of the ice and the uh, freezing of the water rate becomes equal. Ever see that? So that is called the solid ice equilibrium or solid liquid equilibrium. Solid liquid, not solid ice, or ice water, or solid liquid equilibrium. Yes. Equilibrium is so important concept. Yeah. So look here, like that. So solid, you have a solid there and it's melting to give liquid, and at the same time you have some liquid here in the beaker that are freezing, and then let's say 5 molecule of solid are decomposing to give the liquid in 1 minute time, and 5 molecule of the liquid are coming closer to give the solid at 1 minute time. So that is called the solid liquid equilibrium condition. Everybody got that? Time is very important here. Yeah. So you have a clock, and how many molecule of the ice are giving water? Oh, that many molecule of ice are breaking to give liquid. So that one is called the equilibrium. Does that make sense? All right. Now let's go here. So when the solid become liquid, we call that as a melting, and when the liquid convert to solid, we call that as a freezing. Everybody see that? So when liquid becomes solid, we call what? Freezing. When solid becomes liquid, that we call that what? A melting. Melting. That's very simple word. Now let's look here. Liquid solid phase changes. So freezing is a conversion of liquid to the solid. Yes. What is freezing? Freezing means, so you have liquid and you put this in refrigerator, that becomes all ice. So you freeze the ice, the liquid to ice. Ever see that? Liquid become solid. So that means the freezing. Yes. I already discussed that one. And the melting, what is melting? So take out ice from the refrigerator or freeze and put in the room, and then that freeze the liquid, the ice become liquid. That's called the melting. Yes, that's the definition. You already know this kind of thing. We are just doing some systematic study here. Yeah. All right. So let's go down. Sublimation. What is sublimation? Have you guys seen mothballs or no? Mothballs. Mothballs, or so if you remember, so if you go to the bathroom, they put a lot of this white kind of the small balls so that the smell doesn't come out. Yes. So bad smell takes away by these mothballs. Yes. So sometimes they call phenolphthalein, whatever, not phenolphthalein, what they call is a naphthalene, not phenolphthalein, naphthalene. Yeah. So they call that one. So if you, they smell really bad because they want to put there in the bathroom or in the backyard, so that the bacteria or the moth or the flies go away. They don't come. Yes. So if you look there, so these guys, this kind of the solid. So if you, so take some mothballs, So you can just Google and look what I'm talking about, mothballs. Yes, if you look the Google mothballs there, yeah, and put those mothballs here and heat them. When you heat them, put in the oven. When you heat them, you don't see liquid here, no liquid. So normally when you heat solid, they become liquid, right? So it doesn't become liquid; it directly become vapor. Directly become vapor. This is solid directly changing to vapor. It is called sublimation. No liquid phase there. Everybody see that? Yes or no? Yeah. So that's like that, sublimation. So under certain conditions, substance directly go from solid state to the gas state, and they are called the sublimation. Here I have the solid mothball. When I heat it, directly I see the gas. There is no liquid. So this is called sublimation. Yes. Good. Now, if you cool this vapor, so this is a vapor. If you make cool this vapor, you don't see the liquid. Immediately it becomes the solid. It becomes the solid. Everybody got that? So mothballs. So if you hit the mothballs, you got the vapor. When you cool the vapor, it becomes the solid again. Yeah. So this condition is called the sublimation. Everybody got that? Yes or no? Yeah. It's very simple. So no liquid phase with this guy. Solid become gas. Gas become solid. Yes. All right. Now energy changes in the physical transition. So molar heat of fusion. What is fusion means? Fusion sometimes is called melting. Melting. Suppose you have the ice. Suppose you have the ice and you heat it and it becomes the liquid like that. So it is called melting, is called fusion. So what is molar heat of fusion? So take 1 mole of ice. Take 1 mole of ice. Ice, how much is this? 1 mole. 1 mole means how much? 18 gram water. 18 gram ice. You see that? Molar mass of water is 18, right? If you look the periodic table, H is 1, O is 16, 2H and 1 is 18, right? So take 18 gram of ice and heat it. And you need to melt all that 18 gram. And how much heat you supply there to melt that one? That is called molar heat of fusion. Everybody got that? How much you should take? 18 gram for water. For other, its own molar mass. Got it? So that's what I'm saying. Look here, molar means take 1 mole. 1 mole of anything. If you are talking about the water, take water. Molar mass of water is 18 gram. So take 18 gram ice here and heat it and convert them all to the liquid. And then what amount of heat you put there to make that one, that is called the molar heat of fusion. Everybody got that? All right. Now, so sometime the more, and then let's talk about the vaporization. What is molar heat of vaporization? Same thing. Take liquid here. So this is liquid. Again, I'm talking about the water. 18 gram water. How much water you need to take here? 18 gram. And then heat this so that all this liquid becomes vapor. Ever see that? Molar heat of vaporization. You need to take 1 mole and convert everything to vapor, and how much heat you supply at that condition, that is called the molar heat of vaporization. And we need to define the molar heat of vaporization at about the boiling point of the temperature. Boiling point of the liquid. Everybody got that? So that 18 gram is very, very important there, yes? Or you can take the 1 gram water and you can say the heat of vaporization per gram of the water. Either you can express in terms of the 1 mole or you can express in terms of the 1 gram. Everybody got that or no? It's pretty simple, yeah? How much heat you supply so that all 18 gram of water go to the vapor. Or if you are taking 1 gram of water, you need to supply heat there so that all 1 gram of water should go to the vapor. Got it? Like that. Good. All right. So now let's look here, two number. If you want to melt ice, you just need 333 joule for 1 gram. You see that? So you have a 1 gram ice, you want to melt. How much heat you should give? 333 joule. Very small amount. 330 joule is not that big. So take out from the refrigerator, put it here, it itself become liquid. Yes? So 333 is not much. But look here, if you want to boil 1 gram water, you need to put 2260 joule. So boiling water is very hard because you need to give a lot of it. Keep heating, keep heating, keep heating, keep heating, and only it becomes vapor. Everybody got that? Which is easy process? Melting ice easy process or boiling water easy process? Melting ice. You just pull out from the refrigerator and put in the table. It does itself, right? But if you want to boil, you need to keep heating, keep heating, keep heating until all water becomes vapor. Yeah? Everybody got that? So heat of vaporization of water is really high. So now let's talk about some other kind of the forces between the liquid molecule. Now let's look here. I'm going to put one guy here, F. So this is the I already told you 1 2 3 4 5 6 7 8 1 2 3 4 5 6 7 8. You see that? So something like this is a covalent bond. 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8. Last class we did this in the Lewis dot formula. You remember that? So this guy and this guy are same, like gall or boy. No polarity there. Yes? No polarity there. So this is one molecule of F2. Now if you have another molecule of F2 here, 1 2 3 4 5 6 7 8, 1 2 3 4 5 6 7 8. So if you look there, both sides they have 8, right? Everybody see that? So this guy, if we are putting the fluorine molecule in a box, so this guy is pulling this guy is pulling this guy. They don't have plus or minus sign. So this guy doesn't have plus. No. This guy doesn't have minus. No. This guy doesn't have minus. No. This guy doesn't have plus. No. How do they are attracting each other? So that kind of the force is called the London dispersion force. Everybody see that? There are molecules, they don't have plus and minus, but still they are attracting each other. For example, we are similar to guys in we are still attracting with certain force. You see that? So that force is called London dispersive force. Does that make sense? So how does that London dispersive force come? So imagine that I have a long hair and I'm just going like this. So I don't have plus or minus. Yes. But if I'm going very fast with my bike, the air from this side just take my hair back, right? It is here. So momentarily I have some negative charge this way, positive charge this way. You see that? So this time my head is so nice. You see that? No positive, no negative. Yes. But if I bite, so the air just try to push my hair back, and my hair goes this way, and there is no much hair this way. Yes. So that kind of the condition arises in this one. So when this guy and this guy are moving, this passes this way, this passes this way, and this electron just this electron disturb this electron disturb this electron, and there is a lot of electron one side, there is less electron on the other side. So momentarily they create a positive and negative charge. Everybody see that? Yes. So nicely, look here how the electrons are nicely distributing. But if this guy and this guy are passing to each other, how they do this is, these electrons are moved this way. So there will be no electron there momentarily, just so momentarily. I just look here, momentarily when they come near, momentarily this electron go more toward this, momentarily, just for few seconds, few nanosecond, all electron move this side. So this becomes plus, this becomes minus. You see that? You see that? Too much electron is minus, too less electron is plus. Yes? Momentarily it becomes like that. And during the process, maybe this guy has a momentarily a lot of electron, this one, this side, and not many electron this side. Not many electron this side. Where did it go? All right, so I think it just took my everything there. I don't know what happened here. So let's look. So London dispersive force means momentarily. What happened is momentarily. So what I was trying to tell you is that, so like this. So this is fluorine, another fluorine. So all these electrons are uniformly distributed, eight electron. And here also uniformly distributed these electron like that. But when this guy and this guy pass this way, momentarily these electron are more this side. So this become minus. Momentarily there are not much electron. That becomes plus. Momentarily this guy become negative because this side has too many electron. Momentarily this guy become plus. And since this is plus, this is minus, this guy and this guy attract each other momentarily, but immediately that disappear. Everybody see that? So that is called the London dispersive force, and this is the weakest force that exists in the molecules. Yes, momentarily the plus and minus charge momentarily appear and immediately disappear. Good. So where do we find that one? Like the non-polar molecule. These are found in non-polar molecule when the atoms are similar. Like this is a gall, this is a gall. So if this is a non-polar system, but if they are attracting with each other by some force, that kind of force is probably the London force. Everybody see that? So non-polar. But if this is a boy, this is a girl. So if they are attracting with each other, probably boy is a plus and girl is a minus, and there is a strong force of attraction between them. Just like that. Ever see that? Yes or no? All right. Good. Like this. So no polarity. So temporarily, quickly plus and minus appear in the body, and in one, and in another molecule quickly plus and minus appear, and plus and minus of the two molecules interact and they attract each other quickly, and they immediately disappear. Everybody see that? Quickly, momentarily. So no dipole, they have no plus and minus. So dipole dispersion, I just London dispersion, that's called London dispersion. Now dipole forces. Now if you look here, HCl, this is polar, and if you look here, this is polar. Like this is a boy, this is a girl, this is a boy, this is a girl, polar condition, and this is always negative, this is always positive, this is always positive, this is always negative. You see that? Now this positive and this negative attract each other, and that is called the dipole force. Everybody see that? Yes or no? Go. Dipole plus, always there is a plus, not a momentarily. Always one end is plus, always another end is minus. So plus of one end of one molecule attract the minus end of the another molecule, and that is called the dipole force. A little bit stronger. Ever see that? Yes or no? Yes. All right. Now let's talk about the hydrogen bond. This guy, hydrogen bond. Now for hydrogen bond, not many molecule can form hydrogen bond. Either it should have the NH bond or HF bond or HO bond. If there are these three kind of bond, only hydrogen bond is possible. It's a very special case of the polarity. What is the condition for the hydrogen bond? You should see NH, you should see HF, or you should see HO. You got that or no? Make a note. Yeah, I will put this in the exam. So look here. Now, if I look here, HF. So this is HF, and there is another HF molecule. So look here. F has a large negative charge, H has a large positive charge. This has large positive, F has large negative, very large, very large, very large. And then there is a force of negative end of one molecule to the positive end of the another molecule. That is called hydrogen bond. Everybody see that? Very special case of dipole force. Dipole force I didn't talk. So as long as there is a plus and minus, that's a dipole force. But that molecule is a dipole, and they have this condition Hn, Hf, or Ho. In that case, we call the hydrogen bond. Everybody see that? So hydrogen bond is the special case of dipole force. You see that? For example, I didn't tell you this is a hydrogen bond. HCl, HCl. So this is minus, this is plus. This is plus, this is minus. They are attracting each other. Did I say this is a hydrogen bond? No, this is not hydrogen bond. Only dipole force in this molecule. But when you see HF, HO, or NH in molecule, you need to call that dipole force as a hydrogen bond. Who didn't understand this concept? Everybody got that? Yeah. Hydrogen bond is the condition for the dipole forces, but there must be HF or NH or HO. You got it? All right, so like that. So let's go here. Now, what is dipole force? I already told you. Let's say S, O, O. Is this a molecule polar or non-polar? Are they different or same? Different. You see that? So O, and you have a electron there, so it's a different guys there. Around S you see different guys, so these are different. This and this are same, but there is a difference. So this difference make this guy is a polar. So O is always minus, S is always plus. Look here, O is, and that one is a SO2. So if this is a S, this is a O, this is a O. So S, O, and you have a tiny electron there. So this guy is always plus, these guys are always minus. There is always plus and minus. You see that? Now if there is another molecule, S, O, this is plus, this is minus, and this minus and this plus attract each other by plus and minus force. So that is called the dipole force. We are already talking the HCl. Everybody got that or no? Yeah, same thing we are repeating. Now let's go here. SO2, is it polar or not? Look here, there is a 2 electron, there is a O, there is O. So this guy is a polar. So there is a dipole. How about this guy? Now C, now if you look here, H, Cl. Are all groups same or different with the around C? Same or different? Different. So polar. So these molecules attract with each other with a strong plus and minus force. Everybody see that? Now look here, this one is same or not same? Look here, so P, this is Cl, PCl, and there are 2 electrons. Different or same? You see that? Different or same? Different. This molecule is also polar. Yes, so this same, but there are 2 electrons there, they are not showing there, that make it polar. Everybody see that? So this side is a plus, this Cl are a minus. So this kind of the molecule always attract with the polar force. You got it? All right. So now let's go here next. Now this one, BF3, look here. If I look this BF3 molecule, Now BF3 looks like this. So if I draw this one, BF3. So I'm drawing this guy. BF, F, F. Now look here, is the same or different guys around B? The around B is same thing or different thing? Same. There is no dot here. Yes? So the same. So all group are same. So this is non-polar. So if BF3 and is attracting another BF3, that's the London dispersive force. No polarity. Does that make sense? So they are not showing the structure here. There are 2 electrons here. They are not showing. There are 4 groups. Is clearly seeing. They are not showing 2 electrons. So that are polar. This guy is not polar. You see that? So this guy doesn't have the polarity. So no. Make sense? Good. All right. But in exam, I will put something like that. I give here P, Cl, and I also put this one like this. So you just look around, polar or non-polar, you can identify. Yeah. If you see everything same, you should say non-polar. If you see something different around central atom, you should say it's a polar. Ever got that? Same means non-polar, different means polar. Yes? Aaron, any question? No? All right, so let's go here. Now hydrogen bond, I already told you, there is must be 3 conditions. You must see either NH or OH or HF and they qualify as a hydrogen bond. Otherwise, they don't qualify as a hydrogen bond. Make sense? So look here, I draw this HCl and then I draw another HCl here, like this. And then I put plus here, minus here, plus here, and there is a force of attraction between this one. Can I call this guy hydrogen bond or no? No, that doesn't qualify as a hydrogen bond. To be hydrogen bond, there must be NH, OH, or FS, but there is a HCl, not HF. You got it? Yes? Now let's look here. Water. So OH. Is there a OH bond? Of course OH is there. You see that? OH. So this qualifies as a hydrogen bond. Now draw another OH. So OH. This is another water molecule. So this guy is a big plus. This guy is a big minus. O is big minus. This guy is a big minus. These guys are big plus. So since they have the OH and then they attract with each other, so this qualifies as a hydrogen bond because there was a OH in the molecule. You got that? So if you see NH, OH or HF, you need to call that polarity as a hydrogen bond between the 2 molecules. Does that make sense? Very, very strong. Good? All right. So all right, so let's go here. So here, this is a water molecule. You see here, H is a big plus, another H is a big plus, another O is a big minus, this is a big plus, this is a big minus, this is a big plus. Now plus minus of one molecule attract the plus of another molecule with some force, and that force is called the hydrogen bond. Everybody see that? But when should we call that hydrogen bond? Only if you see OH, HF, and NH, not other conditions. Good? Casey? Yes? Does that make sense? All right. Now let's go to the next. Now density. Now density of the liquid. What is the density of the liquid? So what you should do is take a little bit of water, go to the balance, and balance, measure the mass in the balance. So maybe this is 5 gram. 5 gram. Yes? And put this in the cylinder, measuring cylinder. Maybe this is about, let's say, 6 gram. Sorry, 6 milliliter. You see that? And then divide this by this and you get the density. Density is equal to, you got the number you got from the balance is 5, number you got of that from the measuring cylinder is 6. Divide that one, and what number you get, that's called the density of the water. You got that? But the same amount you should take. Take a little bit water, put in the balance, you get the mass. And put the same amount of water to the cylinder and measure the how much it shows in the cylinder. You need to take that number and divide the mass number by volume number. Ever see that? Volume is from the cylinder, mass is from the balance. Who did not understand? I think you already did in the lab number 1 of the foundation or Gen Chem in the lab. The first lab is we did the density. Ever got that? Simple, right? So just take some water, go to the balance, get a mass, and put that same amount of water in the cylinder. Read the cylinder, how many milliliter, and divide that mass number by the volume number, you get the density. Ever got that? The density of water is less than solid, always more than gas. Ever see that? So dense, the solid are very dense, very heavy. So solid are very heavy, high density. Gas are very light, low density. And the liquid are in between. So the liquid are more heavier than gas, less heavier than solid. So the density of the liquid is lower than a solid, higher than gas. Ever got that? Heaviness. Ever got that a little bit or no? Yeah, all right. So you can put, so if the molecule are coming very tightly, we call density high. If the particle or the molecule are a little bit far, density is low. If these two particles are very, very far, we call the density is very low. Yes? Everybody see that? So you can see here. So if it is a gas, particle are like this, far away, density is low. If this is a liquid, if you liquefy this, the particle comes close like that. So density is high. So if you solidify them, they just tightly packed like that, and we call the density is very high. Ever see that? Let's go there. Viscosity. What is viscosity? Do you guys eat honey or no? Honey. So is it easy to pour the honey from the bottle to the cup? No, right? It's a hard. So high viscosity. But water you can easily pour, right? So that's a low viscosity. Everybody see that? So the liquid is in the layer. So if you look the honey, let's talk about the honey. So this is one layer of the honey. This is another layer of the honey. This is another layer of the honey. Liquid is in the layer. But if you look the water, this is one water. One. This is another water layer. This is another water layer. So this water layer is trying to move forward. This water layer is trying to pull this forward moving guy to backward. Ever see that? So this force is low in water, low. But if this guy in the honey try to go fast forward, but the lower layer pulls this guy more toward backward. So this is called the viscosity. So the one layer of the liquid resists the flow of the another layer of the liquid, and that resistive force is called the viscosity. Ever got that? So honey has a high viscosity. One layer is pulling the another layer more toward it, so it cannot flow easily. But the milk or the alcohol or the water moves easily because the lower layer is trying to pull the upper layer back, but it cannot pull with a more force. Ever see that? So that's the viscosity. So what it does depend. So it's basically these are the molecule. So if this molecule and this molecule are tightly attracting each other, liquid cannot flow easily. But if this molecule and this molecule are not attracting each other tightly, they can easily flow. Ever see that? For example, if Casey and me want to walk here, or so I want to go fast, but we have a hand. So if he is holding me very, very hard, can I move fast? No. So that condition is pulling me back with a more force. So high viscosity condition. Yes. But if he and me, he is holding me gently, and I want to move, so he cannot pull me. So I just move. You see that? So if the intermolecular force is low, viscosity is low. If the intermolecular force is high, one layer cannot move fast, breaking another that force. This is just a simple concept. Yeah? Ever got that? So in the exam, I might define the viscosity. So you may not know what is viscosity, but you can definitely know honey is more viscous than water, and you get a point. Yes. So anything is good as long as that makes sense. Yeah. You got that? All right. So sometimes I just want to see if a student can write in language or not. A lot of students cannot write exact language, but they know, oh, honey is more viscous than water. So that means they understood something.
Would you get full credit for response like that?
If the whole class was weak, I used to give the full. But a foundation and organic class is generally strong, so maybe 70. Yeah. So foundation class is normally strong class. Yeah.
So everyone should dumb down.
Yeah, so try your best, but doing something you get the credit. Yeah, because you understood things. Yeah. So you pass. 60 is passing, you got the 70 by saying honey is more viscous than water. Yeah. And then that's a lot, right? Yeah. Now let's look the surface tension. What is surface tension? Now surface tension. Let's look here. I make a slide here. Yeah, these are the definition, and you need to just look. Now let's look the surface tension. So I don't know if you guys have noticed or not. I'm going to show you here. So this is a thin tube like that, and you put water in this one, water. So if you put water here, does this look like this? Nice like this surface like nice like this, or it look like the water look like this. Have you guys noticed how does it look like? Does it look like this surface look like this, or it look like this? How does it the water look like? Exactly. He noticed already. You see that? So this is called the surface tension. What is surface tension? This is a surface, right? Yes? Surface. And this guy, the surface is feeling tension down. Tension means pulling. So surface tension. Everybody see that? Yes or no? What is tension means? I am being pulled by somebody too much. He's giving me too much pressure, too much tension. You see that? So look here. The surface of the liquid, surface, not the inside, just the surface I am looking. Everybody see that? The surface of the liquid is being pulled as if it is uh, it is the stress rubber membrane, like a rubber. Somebody is pulling the rubber down. You see that? So that phenomena is called the surface tension. You got that? So if you have the water in the beaker, normally you can see this in the thin tube like this. So if you put water in the thin tube like that, the surface of the water is being pulled inside more. It's not a flat surface. It's a dipped surface. So it looks like somebody is pulling the water surface from inside down. Yes. So this is called the surface tension. You got that? Both are water. This is also water. This is also water. I was asking, is this good or this is good? What do you see? You see this one. So what is happening here? The surface water is being pulled down as if somebody is there pulling this water down in the surface. You see that? So that is called surface tension. Yes. Why that surface tension arises? So now let's look here. So if you are looking the water here, the water look like this. The water surface look like this. You see that this surface is like behaving as a membrane there, stress membrane down. But it's not like this. Not like this. Yes? Why is that? Because there is a water molecule here. You see, there is a water molecule here. There is another water molecule, 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 another water molecule. So this is guy is pulling down, this guy is pulling down, this guy is pulling him down, pulling him down, pulling him down. But there is no water molecule in there to pull him up. Therefore, this guy is net pull is toward down. Ever see that? Yes or no? Yes, exactly. There are all people are down. They are pulling everything, trying to pull down. There is nobody trying to pull that guy up.
Why isn't it pulling it evenly down?
No, they are pulling because if there is that's a molecule there, and this is they are also pulling it down here. You see that? But you might be saying why it's here and why it's up here and why it's down. That is your question, right? So think about. So let's see. You have this guy. Do you know the trampoline? Have you played the trampoline? I used to jump a lot trampoline when I had some health condition for the exercise. So if your trampoline he is here, you are jumping there. So if you are here, uh, this guy going like this way. You see that? Yeah, this is always up there. Yes? So it's just like the trampoline behavior. I mean, there is a reason I could explain a lot, but I don't want to explain here now. Yes? Because there is a glass surface here. These glass surface are pulling these guys toward this one, not allowing them go down. Ever see that? Why trampoline in the wall doesn't go down? Because there is that you have tied this trampoline here, so that force is a lot, so this is not going down that much. Yes, but there is nobody to hold this guy, so this part goes down. It's just like the trampoline behavior. Ever got that? Good. And why is the surface tension arise? I already told you. There are a lot of molecule down, so they are pulling the surface molecule of the water down. So there is a net downward pull. There is nobody to pull you up there. Yes. So I can give you tension if I want. So I make a very very hard question, and I can make everybody fail. So you feel a lot of tension. You see that? Surface tension, yes, but I cannot give the tension. But I give make simple question, whatever I do, I put this kind, so everybody feel the teacher is trying to pull us up. It's just like that. Everybody see that? If somebody is there to try to pull you up, life is much easier, right? So but for this guy, there is nobody to pull up there are no water molecule here to pull this guy up. You see that? But there is no surface tension here. There is no tension. This molecule have this in the middle here, because there are other water molecules. You see that? This guy is surrounded by other molecules, and this is being pulled this way. This is being, so all the side it is being pulled. So this guy is not feeling any pressure or any stress any side. You see that? For example, Casey is sitting there. Two people are here, and I'm trying to pull him this way, and two people are there, and they are trying to pull him that way equally. He doesn't feel any pressure. So he's there, and he's not experiencing any force. So he's not coming this way, he's not going this way. Force is balanced. It's just like the tug of war. Have you seen tug of war, the game? So there is a rope, so 10 people stand this way, 10 people stand that way, and they pull, right? So if they are pulling equally, the middle of the rope is always right there, yes? But these people, if there are 11 people, easily it goes like this way. So surface tension is like this, tension is like this. Make sense? Tension is a force, yes? But we are talking in the surface, so it's a surface tension. Everybody there? Yeah. Just the word, yeah? English word tension. Tension means force. Good? All right. Surface tension. Again, if the intermolecular force is more, if somebody is down there pulling too much, surface tension is more. Yes? Everybody got that? Yeah, surface tension is more when the intermolecular force is more. That's a surface tension. Greater the intermolecular force, greater is the tension. Meaning that if somebody is pulling with too much force down, the surface is too much stressed, like a rubber or like the balloon. Make sense? Yes? All right. So let's go here. Now if you hit it, so let's look here. There is a one thing here. Surface tension decreases as temperature increases. Let's look here. So let's put the thermometer here in this water. You have a thermometer here, and this thermometer is, let's say, 10 degrees centigrade, and then this surface is depressed like too much down like that. Everybody see that? 10 degree. But if you have the same system and let's say it's a 25 degree centigrade, the surface is tiny, shallow. 25. Everybody see that? Yes or no? So when the 25 degree centigrade, this dip is tiny dip. Here, the surface is tiny dip. But here, the dip is too much. Low temperature, that depth is too much. Everybody see that or no? Look here. So if it is a 25, if I cool this in the fridge, this guy look like this, maybe 5 degree. If it's a 25, the depth of this depressed part is this much, very tiny, this part, 25. But if it is a 5 degree, too much depressed down. Ever see that? Got it or no? So let's go to the next one and draw a picture. So I have this tube, and let's say this is at 25 degree centigrade, this is at 5 degree centigrade. I have water here like this, I have water like this. So this is a 5, low. So if temperature is low, too depth, it looks like too deep like this. But 25 is high, so tiny depth like this. That's what I'm saying. You got it? When the temperature is high, that surface tension is not much. The water is trying to go up. So that surface is not too depressed. Everybody got that? High temperature, the depth is small. Low temperature, that depth is too much because he's being pulled too much down. Yes? Good. Now let's talk about that surface tension. Yeah. So I'm not talking about this slide here. So now let's talk about this slide. This is a capillary action. So you already know capillary action. So if you have the transparent Coca-Cola Coke in cup, this is a cup. So inside this cup you have a Coke, and then let's say this much is a Coke. Now if you put a tiny capillary tube straw here, the layer is here, the water surface or the Coke surface is there, but you will see the Coke rises up a little bit up to that surface. Have you ever anybody noticed that? No? Ah man. Look here. So if you have a Coke here, Coke. So Coke surface is here. That much Coke you have, right? Now you put a straw there. Straw you want to sip, yes? So if you see there, you have not sipped it. So already the Coke is, this level is here. So there is some force that is pushing the liquid up in that capillary. This is called the capillary action. Yes, you already know it, but you have not maybe studied. Yeah, you got that or no? Yes. So what is capillary action? So so you are going to say, oh, there is a Coke or the water or the liquid in the cup, and I put a straw there, and look, the level of the water there, and the level of the water in the cup is down, and the level of the water in that capillary straw is higher. So this action is called the capillary action. Can you define this one? Yes. So you can just, it's simple, right? Yeah, describe whatever is there. Yeah, Coke. Yeah, how we do the drink the Coke. Yes. Now what is this showing here? Look here. So the capillary action I already told you. What is this showing? Which straw is very big? So this straw is very big. This straw is a little thinner. This is the tiniest, right? So if the straw is tiniest, the level rises too much. Yeah, that's what it is saying. Everybody see that? Yes. So you can try in home. So put a Coke or water in the beaker. Take thick size, this is one size, another size, thin size, very thin size straw, put it here, those things. In the very big one, water level rises this much. A little thinner, water level rises even bigger. In the very thin, it rises in the highest. You got it? Yeah, that's like that. So let's look here what they are saying. Capillary action is the ability of the liquid to flow up in the narrow tube. So opposing the force of gravity. So Earth is trying to pull this water down, and this wall of this capillary is trying to hold this water up. So this is the two forces are acting, and this this is winning. Everybody see that? So if I want to climb this, I don't want to do that. I want to climb this wall. So Earth is trying to pull me down, and I want to I can climb this one. How can I climb that one? Because I have too much force to the wall. I can stick, then Earth can pull me down. Therefore, I can walk. Everybody see that? So there are a couple of forces are working in against. There is always Earth is pulling this down, and then this tube, and there is some pressure from the air here. They are trying to hold this molecule going up, and there is some force, and that force is holding those molecules there in the structure. Everybody that? Yeah. So while you are climbing the tree, can you climb the tree without holding the tree tight? You cannot, right? So you need to hold the tree tight so that earth cannot pull you down, so that you slowly slip off. Yes? It's just like that. Good. So I already told you, if the tube is smaller in diameter, liquid flows up more. We are done with the this liquid. Now let's look the another chapter 11. So how much time we have? 3, 1. So